in 3. Urdu countdown, please, Eric.
I'll do it in Turkish.
Okay.
4.
I always like to know how to say countdowns in any language possible.
Well, there's that old Tom Lehrer line, in German or English, I know how to count down, and I'm learning Chinese, says Werner von Braun.
Very good. Okay, we are now live with Doctors Weinstein and Wolfram. Welcome, gentlemen. I'm going to just publicize that we are going live, and I will then ask us to introduce ourselves, and we'll get started. We have graciously been joined with two of the most prominent and two of my real heroes in this field that are maverick mathematicians who are self-made mathematicians in a way. And I want to talk about how they view the current spirit of the times, the zeitgeist, as we say, in terms of theories of everything that are percolating around in the atmosphere. And to begin with, I'll ask my guest Eric to introduce yourself and say a little bit about where people can find you. We'll do that right up front, and then we'll get started with our discussion topics. We're gonna have a nice, clean fight. We're going toe to toe. No, there's not gonna be any fight. It's gonna be very respectful. So thank you both for joining. Eric, can you introduce yourself, and it'll buy me some time to tweet out this link?
Well, didn't I just tweet out the link that I just saw you tweeting out? Or
oh, you did? Perfect. Okay. Phenomenal. Okay, great.
Check my feed, Eric Weinstein. I'm managing director at Teal Capital. I come from a mathematics background, so I'm not a physicist, and I have an eclectic podcast called The Portal, which I hope to have. In fact, I've got agreements from both of these gentlemen to be my guests on The Portal, so I'm really looking forward to that and happy to help blow up into the impossible. Brian, you're doing a fantastic job.
I love it. And it's all thanks to you guys. You guys were actually my first guest in what I call the pandemic podcast series, which began back in April, actually late March with Stephen. It was the first of the two of you to come on the podcast and really kicked off this whole idea of getting some of the world's most brilliant minds to engage around this topic of understanding the fundamental nature of the universe. And at that time, because of the pandemic, perhaps Stephen's schedule was amenable to coming on my podcast. So we chatted for a mere 3 hours or so. And he's, as I said, gracious enough to come back. Stephen, where are you joining us from today?
I'm in Concord, Massachusetts. And do I introduce myself? I'm Stephen Wolfram. I do science and technology and things. I built some technology things lots of people use. I built some science lots of people use. And about 30 years ago, well, I used to be a particle physicist long ago. I did that when I was a kid. And then I got interested in computation and have kind of alternated between doing basic science and doing technology. And I've now done about 5 cycles of that. And I think it's a very interesting process, actually, alternating between basic science and technology, because they kind of build on each other, and it's sort of a progressively spiral upwards, so to speak.
Yeah.
But the big surprise for me was about a bit more than a year ago now, a bunch of things that I've been thinking about how to make a fundamental theory of physics. Actually thought, I think I actually have some way forward. And a couple of young physicists were really enthusiastic about working with me on it. And so we're like, okay, let's try and really do something. And the huge surprise is that it's worked, and which I didn't expect.
Yeah.
I mean, it's you know, we're at 100 years roughly for, you know, general relativity and quantum mechanics, which are the two sort of big achievements of 20th century physics. And, you know, they've taken us a great distance, but, you know, I had a bunch of ideas that have been sort of based on things that came out of the whole computational thinking that I've done. And anyway, the big surprise that's worked, and not only did it seem to have worked when I last talked to you, it's been going absolutely spectacularly since then. And it's kind of like embarrassing, because there are a lot of things I should have been able to figure out 20, 30 years ago, which are now becoming obvious. And I think one of the other things to say is that one of the surprises to me is that I had thought we were building this kind of prong in the direction of kind of computation that would be really different from the mathematical physics and so on that people had done before. Turns out we basically built a sort of a low-level machine code for how things work. But it turns out an awful lot of the formalisms that people have worked on in mathematical physics the last 50 years or so, they actually fit beautifully into the kinds of things that we're doing. And they seem to kind of illuminate what we've done, and hopefully what we've done illuminates what they're doing. And actually, my favorite analogy in recent times for this is what happened in early days of computation theory with things like Turing machines, which was that people had come up with, models of computation, combinators, lambda calculus, general recursive functions, things like this. But it wasn't clear how they fit together, and they all seemed rather abstract, and people couldn't kind of tether them. And then Turing machines came along, and in the usual way that science history is done, we could say immediately everybody understood. But actually, it took, let's see, how long? 40 years, 50 years? So immediately it was actually 40 or 50 years. But people understood from that kind of more concrete tethering of these ideas about computation, how all these different things fit together. So that's been. I mean, it's both scientifically interesting to me, and I think also sociologically interesting, because often, you come in with the big new theory, so to speak, and it's like you're kind of gunning down everything else, but that's not what's happening here. I mean, what's happening here is that we've got something which is sort of orthogonal to what other people have thought about. It's kind of a low-level machine code, and we can kind of see how things fit together at a higher level. Yeah, anyway, that was my long, short introduction.
That's your elevator pitch that goes to the space elevator docking station. Thank you, Stephen. And both of you guys are notable, as people are pointing out in the chat, which I'm monitoring. So behave in there. I am seeing a lot of questions from younger people, and I think the two of you in particular have an ability that other scientists have not yet really been able to achieve, which is to engage young people. And Stephen, you just talked about engagement by these young physics students that you and I spoke about in our first conversation back in April. And with Eric, people are engaged on Discord, on comments, and people all over the internet are really engaged with it. What do you think it does? This podcast, the Into the Impossible podcast, I like to fashion myself as, someday I'll be the Joe Rogan of physics. There's already one Joe Rogan, but I'd like to know, what is it about these theories of everything that really engages young people? And what I want to do is kind of translate.
It's fascinating that you have this sort of bucket, theories of everything.
Yeah.
I don't kind of view it as a bucket like that. I think it's a for me, I spent my life basically developing computation, and the fact that I happen to have discovered that relates to kind of fundamental theory of physics is kind of a singular event as far as I'm concerned. The kind of the bucket of theories of everything is not a bucket I particularly identify with.
Right, and if I can agree with
what's that?
If I can agree with Stephen, there can only be one.
No, that was what I said today.
Actually,
there's
Eric,
a Highlander, sponsored by Highlander.
That's one of the surprising things that we've discovered, is that really isn't true.
So there can be many ways of approaching that theory.
Yes, but the thing that's interesting is that you could say there's only, fair enough. I mean, it depends what you mean by only one. That's an interesting kind of ontological, epistemological question. But I mean, it's like, you could say about computation, there could only be one theory of computation, and it's Turing machines and its general recursive functions. The thing that's surprising about physics that has become increasingly clear is that there's this notion of, what are the underlying rules, and then how do we observe those underlying rules? And it's becoming clear that you can basically, the only thing that is absolutely rigid is the underlying rules are computational and not hypercomputational. That is, once you say that the underlying rules are purely computational, it then follows, it seems, that the things we observe from 20th century physics are inevitable consequences of that and a few other unspecific assumptions. There are more. This is a hard thing to explain, and actually we're just, I think, Okay, so here's a remarkable connection that's just been becoming clear. So we have this notion of, you have some underlying rules, you follow these rules, you reproduce how the universe works. But on the other side of that, we are observing how these rules are working and interpreting them to say this is how the universe works. The thing that is surprising is that one can, in the language of our kind of theory, there's this thing called the rulal multi-way system, which is this kind of this branching system that runs sort of all possible rules. We're now jumping into the most abstract, most complicated. But I just want to say one thing about it, which is kind of interesting, which is it's turning out that this incredibly abstract thing that we have, this rulal multi-way system, appears to be the same as this thing called the infinity groupoid, which was developed by Grothendieck in, when was it, the 70s, I guess, 1970s, which is kind of a pinnacle of abstraction of category theory and other areas of mathematics. And what is really quite remarkable to me is that it seems like this thing that's coming out of our theory kind of maps into this incredibly abstract mathematical thing. And the observations that we have of the universe correspond to a particular, in mathematical terms, kind of fibration of this infinity groupoid thing. And that basically what our way of interpreting the universe is kind of a slice of that mathematical object. And so it's the statement, there's only one theory. In a sense, all these theories are equivalent, but the question is how we are observing them. And again, this is we can unpack this.
Again, I was making a pop culture reference. The intellectual spirit of it is that you can have a summit, and there are many faces that could be used as assaults on that summit. In the end, however we traverse, Einstein, for example, came up with his divergence-free equations after some rumbling around in differential geometry. Hilbert went, immediately to a Lagrangian description. They were describing something in common. So I didn't mean to suggest that there was a single description, but there can really only be one underlying theory. And all of us who are, and I was trying to agree with you, Stephen, that the most probable number for wrong guests on this live stream is 2. But in all probability, if it is not 2, then one of us is wrong. I'm interested.
I don't think that's necessarily the case.
Well, let me just advance at least so I can make my wrong statement. It strikes me that you have gained confidence that what you are doing is actually not only capable of producing a fundamental final theory, and we can talk about what the right language is. I'm not wedded to any particular description if you have an objection. But it sounds to me like you are increasingly convinced that week by week, this is really the most promising assault on our foundations. Yeah. And first of all, if I'm wrong, I hope that you or Garrett Lisi or one of these other crazy people turns out to be right. Would be a pleasure to lose to you, sir.
Well, the thing is, the thing to understand is the kind of system that we've built. It is very likely that I don't understand what you've done, but I know a little bit of the mathematical background. The whole, for example, understanding local gauge invariance and understanding how fiber bundles work in our systems. As a student, actually, at our recent summer school, mathematical physicist who managed to make great progress on that. And it's actually very clever and much simpler than I expected. The way that essentially sort of fiber bundle type structures and local gauge invariance arise in our theories. Now, what you do with it once it's arisen from this kind of low-level machine code, that's often running with much more traditional mathematical physics. And I don't think that there's it's not an incompatible thing to say, oh, there's some complicated structure to do with, high dimensional systems and fiber bundles and so on. That's not like, there's no divide yet.
Well, let's try to state how you and I could both be fit into the discussion that Brian is trying to conduct.
Yeah, one thing I definitely agree that consilience is nice and it's wonderful to have consonance. What the viewers want as argumentation. No, I'm just kidding. I don't care about that. But what I do think
we should get Sabina back on.
I think would be exactly. I think what would be really a great outcome of this discussion would be kind of the joining of your two different approaches. I don't
know about Eric's stuff, so I can't really comment on that.
No. I mean, the people out that are watching that have, as you just said, fiber bundles, hop fiberation, gauge invariance, how it fits in.
Talk about those things I understand.
Yeah, no, those things you understand, sure. But way of having sort of a Rosetta Stone, if there are people out there, I'm not asking or tasking you guys, God forbid, with homework, but people in the respective domain experts in both of your two categories, I think that would be an interesting kind of project to see, can these be reconciled? Because what if you found out that...
So maybe I should explain what we're doing, okay? Because it's a fairly large effort at this point.
Yeah.
I mean, it's what's been happening, you talk about engaging young people, what I've been trying to figure out how to do this because there's been a lot of enthusiasm for our project, a lot of people interested. A lot of people say, I want to contribute to this project, okay? So right now we're just about to kind of roll out, I think we have 30 research affiliates and junior research affiliates who are mostly people who came to the summer school that we just spent a month having. And they're people who are sort of in motion, sort of doing research along the lines of this project and, producing papers and so on. And, one of the important objectives there's several important objectives, but one of them is making these bridges to other kind of mathematical physics approaches. Another thing is just being able to check off the list. There are, these effects known in quantum mechanics. There are these features of general relativity, for example. Can we go down the list and say, okay, we have destructive interference, we have spin statistics connections, we have this, we have that. The thing that's just absolutely amazing is every time I think one of these is going to be really hard, it turns out to be much easier than I think. And that's been a big surprise to me. I mean, my expectations keep on being kind of exceeded. And I think that the other question is, for example, for something like general relativity, which I know, you have a lovely cosmic microwave background globe in the back there. It's right. That's the
right up there.
It's very cool.
Yeah.
It's weird that it's kind of the inversion of the sky, so to speak.
Yeah, it's
the globe.
God's eye view, right?
Yeah, right. So for example, there's we have a sort of mathematical proof that in some limit we can reproduce general relativity. But the question is, can you actualize that? Mm-hmm. And so here's an interesting example of how sort of, a direction we're going in, which is an interesting sort of way to validate theories, is the following thing. So when people normally study gravitation theory, they say, oh, we've got Einstein's equations from 1915, they work great. But if we actually want to find out how two black holes merge, we don't get to kind of work out with Mathematica or something, the exact, result for, how this black hole merger will work. We have to make numerical approximations to the Einstein equations, sort of break them down into something discrete, solve them on a computer, see what the implications for this process are. But that kind of break down the Einstein equations into something discrete that can be solved on a computer, there's an alternative way to think about that, which is start from our theory, which is born as something that you can run on a computer, and then go up from there to get to something which can reproduce what happens in black holes and so on. And so, this is the kind of thing, I happened to do this years ago with fluid dynamics, where you can start with these very simple, in that case, cellular automaton models of fluid dynamics and build up from those to actually reproduce fluid phenomena. But anyway, so the thing is what I might call proof by compilation, so to speak, which is that you're taking the you're going from the kind of low-level structure of the model to actually do computations that can then be compared with black hole dynamics, even though you sort of know it has to work because you have a mathematical proof that the two things are equivalent. But it's very satisfying to see it actually work. We haven't, done that yet, but we're in the process of doing it. And more interestingly, actually, in quantum field theory, where numerical methods have been much harder to apply, it looks like we have a pretty good way to do sort of numerical quantum field theory in a different way than it's been done before.
When you say it's easy, by what metric or what measure function are you defining that? Easy in terms of just easy for a brilliant grandmaster of physics to unravel, or easy in terms of computational efficiency in some sense?
No, I mean, for example, one of the things is, do we have to know how electrons work to be able to, or do we have to know what photons in detail are before we can reproduce effects in quantum mechanics? The answer is, a lot of these phenomena seem to be more generic than I expected and more amenable to being kind of explained without having that whole tower of features built. So that's the main thing I mean by easier. I think in terms of the technical difficulty and the mathematical depth of what's going on, I mean, we're doing what physicists often do, which is we're skating over many of the mathematical difficulties. I mean, in some of these derivations, there are like 12 different limits that have to be taken of, this thing is small compared to the size of the universe, but large compared to this, but small compared to the curvature of that, but large compared to this, and so on. And, each one of those limits is a significant amount of mathematical work to validate and so on. And this is the typical thing that's been done by physicists through the ages, I'm afraid, that just skate right over those things. Now, we have a big advantage, which is we can do computer experiments. So we kind of know it's going to work. I mean, we know we're not going to be too far off because we can actually check a bunch of these things in actual experiments. Although the experiments we do, if the universe has 10 to the 400, atoms of space in it, we certainly don't have that many in our computer. So we're doing very small versions of this. I want to say that I think it might be interesting for us to talk a little bit about kind of the more sort of societal and structural aspects rather than getting too deep into the
Sure.
kind of.
Wait a minute. I was looking to I wanted to get into the damn weeds.
Go for it. Okay.
We will, but yeah.
Small amount of weed whacking, and then we can talk about the bigger picture of science and the world and so on, which I think we probably both have things to say about.
Mm-hmm. So I think that segues nicely into a question that I brought up with both of you separately and then earlier today, and that's kind of the structure of the way that scientific revolutions take place. And it's become a trope, nowadays to say, there's a paradigm shift, which is brought upon by some new idea, radical, usually some lone genius like you guys, working almost in solitude. I'm just teasing, but
you're just going to get us into trouble with Reddit. That's all you're doing. You're just baiting Reddit.
Well, hopefully Dr. Reddit is not watching yet.
I guarantee you she is.
What do you think about this notion of paradigm shifts? Do you think it's really the way that science takes place, or is it just sort of a retrospective, retrodiction, historical narrative of what has taken place that is just convenient as a hack for the human mind to say, okay, in retrospect, the paradigm shifted with Galileo's observation of the Jovian satellites? What do you, Eric, think about this notion of Kuhnian paradigm shifting?
Well, I mean, you have to have lived through stasis and stagnation and through revolution and boom. And even if the boom isn't the largest boom on record, like, the gold rush or something, in science, I lived through one or two revolutions, one of which was a Rosetta Stone between differential geometry and quantum field theory, or at least the structure underneath quantum field theory that was figured out in the mid-1970s. It doesn't have a historical, like, you can't go to a biopic about it, which is weird. But your friend Jim Simons, Brian, and C.N. Yang, arguably maybe the greatest of living physicists, figured this out over lunch. And that revolution is going on to this day, called the Wu-Yang Dictionary. There was another one having to do with the discovery that quantum field theory was a mathematically natural structure, not just a grab bag of techniques, and that it would have been discovered as an enhancement of something in algebraic topology, since Dr. Wolfram brings up Alexander Grothendieck. In algebraic topology, we have a theory called Bordism, which is an extraordinary cohomology theory, and quantum field theory would be discovered in enhancing Bordism theory, as Ed Witten, Michael Atiyah, and Graham Siegel and others taught us in the 1980s. Having seen revolutions, yes, there are things that you can tell people where they're never the same again. They come to understand, as I've said before, there should be a tattoo on all of our cecums. If you can read this, you're too close. When you pull your head out, you can better understand the world after the revolution. And what Dr. Wolfram is discussing is that we've had a small number of complete revolutions in our thinking and many more minor elaborations in our thinking. There was one around scale, which might be called the first and second renormalization revolutions, originally of Feynman and Schwinger, but then Ken Wilson really was probably the big name in that area. Having been through a few of these revolutions, having been close enough to study them, and also in a few different fields like biology with CRISPR-Cas9 or optogenetics or something like this, yeah, no, these things are real, and they change everything. And my resistance to Stephen's theory will one day turn into my saying, "Oh my God, I can't believe I didn't understand what you were saying. It was too new." To use Feynman's famous quote from when he tried to introduce his path integral or sum over histories approach, he said, "My machines came from too far away," because he was derided. And you see a lot of people, we were talking before about Reddit, just to close this out. A lot of people are trying to figure out what the hell is going on in these live streams and why does one person get to be in them and who's a crank and who isn't. Yeah. They're trying to use some sort of indicia, which is, does that person sound like they're wild-eyed? Does that person sound sober? And it's a really odd moment because on the one hand, everybody sounds crazy and some of the crazy people sound among the most sane. And I think Dr. Wolfram, for example, despite the fact that I think he's wrong, I think that he is one of the sanest voices out here, one of the most interesting for sure. And part of the problem is the mainstream of the community sounds mad as a hatter to me. Dr. Wolfram sounds much more reasonable.
And
okay, so let's comment on paradigm shifts and so on. So I've been fortunate to live through some myself, even probably responsible for some. I think the main process that seems to happen is a methodological advance is made that opens up some new area. There's a bunch of low-hanging fruit to be picked in that area. Lots of exciting stuff happens for 5 years, 10 years, maybe a little bit longer. That area of science gets big. It gets quite institutionalized. It slows down. There's 50 or 100 years of sort of stasis. And then maybe there's some methodological advance and it opens up again. And typically in the, in terms of sort of the conceptualization of these methodological advances, it's usually a long process for the people involved in them. And it's usually, you have to sort of think about things in the right way. And then maybe there's some moment when you realize, yes, I can actually see how this works. Now, for example, in my current activities in physics, one of the embarrassments of that is that the fundamental model, which is based on, you can think of it as based on rewritings of hypergraphs or very minimalist, very sort of abstract thing about transformations for relations between elements, okay? And that idea you can also think of as transformation rules for symbolic expressions. Well, the idea of transformation rules for symbolic expressions is what I've been using technologically in building computational languages for 40 years. And it is super embarrassing in a sense that the core idea, which seems to have unlocked what we're doing now in physics, is actually something that I've been working on for 40 years. Mm-hmm. But I didn't see that connection. I mean, what's happened is that normally in using symbolic expressions and transformation rules for symbolic expressions in computational languages, those symbolic expressions actually immediately mean something. Mm. They mean, adding things together. They mean, I don't know, some other identifiable kind of operation. Whereas in the way we're using them in physics, it's just the infrastructure. They mean nothing. They get meaning because the things in them turn into the things like the atoms of space and so on. But to begin with, they mean nothing. So for me, that's sort of an interesting case because it's something which has been right under my nose for 40 years. Mm-hmm. And it took that amount of time for me to have the right sort of conceptual framework to see how it could be applied in this particular case. And, I think that's, there's also a question of kind of how people, how these paradigm shifts and so on kind of land in the world. Okay, so there's one big one that I've been deeply involved in, which is the whole idea of using computation and programs as models of the world instead of using mathematical equations as models of the world. So you roll the clock back, 300 or so years, we get to Galileo and Newton and so on. And they had the problem of explaining to people, no, you can't just reason about how the world works. You can write down a mathematical equation and solve it, and that will tell you how the moon moves or something. And at that time, it was a sort of complicated battle to have people realize, yes, you can just solve the mathematical equation, it'll tell you how the world works. It's not a question of reasoning about it. Okay, 300 years go by, and then we're at the point where, oh, mathematical equations are the way the world works. Is there some other way to describe how the world works? No, there can't possibly be another way to describe how the world works. So when I started thinking about kind of generalizing sort of rules for how the world works and thinking about simple programs and what they do and kind of exploring the computational universe of simple programs, there was sort of, I would say, actually looking back on it, it's interesting. I published this big book called The New Kind of Science back in 2002. I would say that many fields were really quite receptive to what I had to say. Fundamental physics was actually one of the only exceptions.
Yes, that's
what was interesting there was people. Some people said, oh, programs, we don't need programs to describe the world. Mathematical equations do just fine. Okay, now you look just maybe 15 years later, and if you look at new models that people are inventing of things, they are overwhelmingly based on programs, not based on mathematical equations.
Yeah, but there's a dark story underneath this, which is that as tech has been really and by tech I really mean computation, because most of the rest of technology seems to have vanished. As computation became the one bright spot in a relatively stagnant world, and I hate to say it that way, and there are caveats, but let's keep going. It came to be that many people started to dress up whatever they were doing in terms of computation, right? Because it was possible to seek, funding from a Yuri Milner or a Mark Zuckerberg or, dare I say, a Jeffrey Epstein. All of these sorts of things, which had exotic funding sources or possible prizes around them in computation. It also became the case that funders were more eager at the government level to hear a proposal for something having a computational nature. So the problem that we have is that there were all of these old ideas about, von Neumann, of Schrodinger, of Hawking, et cetera, Turing, about the world as a computer. And at the moment, there's a system of selective pressures that partially has to do with how difficult it is to fund one's research. So I'm very worried about the event horizon of the computational paradigm. It's absolutely true what Stephen is saying, that this has torn through theoretical physics, but I'm very dubious as
No, it hasn't. No, it hasn't. Not theoretical physics. No, it hasn't. That's an area where it has not made great progress. I mean, if you look at other fields.
No, people aren't necessarily doing what you're saying, but they are dressing things up in terms of computational. Yeah.
So I think you're interesting points. Okay. I think not quite right. Okay, so you're absolutely right that in theoretical physics, for example, quantum computing has become this giant, fundable thing. We can talk about that separately.
Or black hole information paradoxes, or the idea of the universe as a computer. John Wheeler had old points, but that feel, again,
but that's not what I'm talking about. That's not what I'm talking about. What I'm talking about is that there is a way of thinking about doing science that says you write down an equation, you can solve this equation, and it will tell you how the world is going to work.
Right.
That's one model of doing
computational scientific materialist.
Well, it's sort of the old line of reductionism, which is if we could just solve these equations, we get beautiful closed form solutions.
So the surprising thing that I really got serious about in the 1980s was this phenomenon where if what you think is going on is that it's just following computational rules, then that doesn't work anymore. There's this phenomenon of computational irreducibility where the system is doing what it does and it's doing a computation, and we're trying to figure out what the system does, and we're also doing a computation. And there's this thing I call the principle of computational equivalence, which is basically the statement or the claim, which we're getting more and more evidence for, that our ability to think through what a system does is of the same level of computational sophistication as what the system itself does. So we never get to outrun the system. We don't get to do what has been the kind of banner story of a lot of traditional mathematical science, which is find this reduction, this reducible computation where we can just say, and the system is going to do this. We're kind of stuck.
Well, there's the issue about whether we can compute it out once we find the rules. So the idea is that you could imagine a world in which Maxwell's equations are perfect, all the way down, and you still might not be able to compute the consequences of Maxwell's equations in
like the Einstein equations, like Navier-Stokes. Same it happens, it happens, but it's very obscure in those equations, because when you look at like the Navier-Stokes equations, the standard equations for fluid flow, one of the most notable features of fluid flow is fluid turbulence. Fluid flows quickly, it looks kind of random. You say to people who study the Navier-Stokes equations, can you reproduce that from the underlying equations? Is that something that's in the underlying equations, or is it maybe a sign of some, smaller scale molecular processes that are getting amplified, et cetera, et cetera, et cetera? So they'll typically get, these days they have a lot of empirical ways to do it, but if you really push on the fundamental question, they'll get kind of embarrassed because they just don't know.
Well, it's like quark confinement. If you know the rules of quarks, can you prove that they are never going to be found in isolation and only going to be found typically in hadrons and protons and neutrons?
That's a similar thing, which actually has that particular one actually has a more direct story of
let's all agree that we're modern people and we don't have the old reductionist dream.
Yeah. Right, but that's a non-trivial point, because in theoretical physics, that point has not yet been understood.
Well, I think it has. I think that the extent to which we talk about what is emergent, what is not, what is anthropic, what is not, we now have many concepts, including Galois sorts of not Galois. Gödel sorts of concerns that are cropping up in theoretical physics.
Finally, yes. I wrote this paper about undecidability in theoretical physics back in the early 1980s.
I think it needs to be said, again, by somebody who hopes to be your competitor, that you were very early on a lot of these topics. You weren't doing it as part of a fad. You were, in fact, the pioneer coming out of the computational ability of Mathematica and all that you've set up. And you've wrapped some beautiful libraries with many more functions than anybody ever thought we could have. So, kudos to you. There was a huge resistance inside of theoretical physics because it was a very closed, arrogant community. It had many reasons to be arrogant. It has fewer reasons to be arrogant now. And so in part, I think that you were dismissed unfairly. It's very important that you not be the one to blow your own horn. So I would be happy to say that I remember when that book came out. I remember the derision, the anger, didn't seem to come from anywhere in particular. And it was not listened to properly, even though I don't think that it actually is doing what you say it's doing now. But one, happy to be wrong. And it was always a really important point that you were making within that. I just don't think that it really got heard.
What do you make of that, Stephen?
But hold on a second. I want to just correct that impression, because the fact is, I was looking at this recently, right? What, sort of insofar as there was negativism about that book, where did it actually come from? Because there was tons of positivism. The negativism, it turns out, was specifically concentrated in people who did fundamental physics. And if you look outside of that area, it was not negativism. It was actually a lot of positivism.
Yeah, but to steel man the critics, which I hate to do, but
what's that?
To steel man rather than straw man the critics. The critics have a feeling that there's a tiny number of fields where it's very difficult to check people. It's very hard to say when a theoretical physicist is bullshitting you. It's very hard to say when a theoretical, very pure mathematician is speaking nonsense. So there is this fear. How do we know that what he's saying, in some sense, is correct?
Correct enough, sorry, Eric, to interrupt, but correct enough to devote many precious hours to unravel it. That's the criticism.
There's that, but there's not that much to unravel at the moment. So I'm not that sympathetic with that. This is sort of Sabine, I don't have time for this stuff. Right. My feeling is, the hell you don't have time. There's almost nothing happening. Now, with that said, what I think is that there was a fear that, quite honestly, people like you and like myself are cheating. And I want to be open about this. Yeah. The fear that comes out of whatever is left of the core community is you guys don't have a right to go direct to consumer. You don't have a right to talk about the field. that belongs to a tiny number, the privilege of a tiny number of people who do this morning, noon, and night, who are all possessed of common beliefs. And that's something that both you and I have been fighting. Now, I would also suggest that Stephen and I probably are not eager to open the door to every lunatic with a red crayon who wants to scribble something on a roll of paper towels and say that they've got a unified theory. So there have to be some standards. On the other hand, the core group that's been trying to gate this has failed.
Well, what do you make of that?
So I have a slightly
sorry,
different
Stephen. Go ahead. I'm sorry. Go ahead.
Yeah. No, I mean, the first thing, so it was historically interesting to me. So I was, I did particle physics during its kind of golden age in the late 1970s, when I was a late teenager, so to speak. And I think I did pretty well. Was sort of pretty successful in the field, and I wrote a bunch of papers that still get cited because I lived in the sort of golden age, and not a lot came after that. I mean, not because they were necessarily, there was a question of picking low-hanging fruit, but I think, and so that meant that I know a large fraction of the kind of leading people in theoretical physics above some age, and so I was quite surprised by the level of kind of angst when new kind of science came out. But the typical thing that I heard was, oh my gosh, if this is right, what we've been doing for the last 50 years all has to be thrown away. And I kept on saying, I don't think that's what's going to happen. But, and people would say to me like, I was noticing, I think I made wrote a sort of historical piece about this, and I described it as Nobel Prize winners with pitchforks. And so there was quite a parade. It's quite kind of interesting looking back on it. I was going to send one of them an email actually, just when my new thing came out, and then the person went and died.
They die or they soften.
Yes. I think that I think what was interesting to me was at that time, 20 years ago, there was a lot of kind of, we're going to make it. String theory is going to do it. We're almost there. We don't need anything else. I think that's changed now.
Well, that's slightly after you left. That's about 1984 through 86 when the string mania was at its height.
Yeah, right. No, I think that, now, we've got a lot of mostly younger physicists who are pretty seriously working on this stuff. And I think, it's going great. Of the older crowd, I sort of been in contact with a large fraction of them. And it's like, oh, this seems interesting. And it's like, you should actually work on this. I keep on telling them, you should actually work on it. And some of them have, been on live streams we've done and things like that. And we've certainly talked about things. But I think, a lot of people, they do something for a living, and this isn't what they do for a living. And I don't know whether they'll kind of make the effort to kind of change what they do for a living. I don't know whether it matters. I think that the concept that, it is probably, particularly 20 years ago, it was still the case that the kind of institutional structure of things like physics was very strong, as in it was like, we have this institutional structure and this is how this field is going to work, and we don't need anything from the outside. My impression is that that's weakened in the intervening years, but maybe I'm wrong.
I think, the perception that I get from comments from people is almost like being candid with both of you as friends. On one hand, Eric is criticized for a complexity, a technical, sort of a toolkit that is beyond even many theoretical physicists. So, I disagree that, they'll say, oh, I don't have enough time, but it is true that there's, general stock and trade of a theoretical cosmologist is not necessarily Hopf vibrations, fiber bundles, et cetera. It might be perturbation theory. It might be quantum field theory. And on the other side of the coin, Stephen, I think sometimes the perception is it's too simplistic, not in the sense, or it's too elementary. It's too fundamental in a sense that you use in your wonderful new book, which you're kind enough to send to me. And congratulations for writing a shorter book than A New Kind of Science, I think by about 40 pages.
How come Brian gets a copy?
I think Stephen will send you one, or I'll give you one when we get together.
Yes.
I've got multiple copies. But Stephen, so let me just start with you for a second. Eric knows his critics. He knows what people say, and I think he brings up a good point.
Wait, I have critics. This is the first I hear of this, Brian.
There's two. One's named Pia something, and the other one. But Stephen, in your case, I think it's absolutely correct that people are blown away by the contributions. I have people asking me to thank you. From the depths of their heart for Mathematica, for new kind of science, that in some ways it's amazing that you guys have, I get comments, I'm reading them. You saved my life. You touched my life. You changed my life. It's so amazing. But on the other hand, I think that in real scientific circles oftentimes breeds a class of almost undermining and
let me explain something, which I think is interesting.
Yeah.
That people think what I've done is simplistic is a great compliment, because I've spent a huge amount of effort trying to take the things that I'm thinking about and make them simple enough that both I can understand them well and I can explain them well.
But
and I knew when I wrote New Kind of Science, I even said this in the introduction. I said, the fact that this appears to be very simple, appears to be very straightforward, will make people who thought, who work on technical science think that, they must really understand this, and this must be something simple and irrelevant. It isn't true. The fact is, it is much more difficult, at least for me, maybe it isn't for everybody, but I think it probably is for almost everybody, to turn things into things that can be described simply than it is to kind of, maybe there's a certain challenge to sort of building up the tower of being able to talk about, fiber bundles and self-dual connections and all this kind of thing. But it's a well-defined tower you have to climb. I mean, I think that the problem of turning things into, so for example, right now, I happen to be working on kind of a very bizarre thing that, again, I never thought would come out, which is a kind of a general theory of metamathematics. So in mathematics, one thinks about, there's the particular mathematics people do, the 3 million theorems of mathematics that have been published in the literature of mathematics in human history. But then there's the kind of full metamathematics of all possible theorems. And the remarkable thing is that it looks like we can actually derive kind of the analog of Einstein's equations in metamathematical space. A very bizarre idea.
So we keep coming to this point. I want to just put a pin here just in case it's of interest. I don't think that it's very difficult to imagine recovering Einstein's equations given Hilbert's contribution, so that we know in a weird sense that Einstein did something very, very difficult. And I've compared it to Half Dome, where there's a sheer face that Einstein went up, and then there's this gentle face that Hilbert went up after he knew that it could be climbed. It seems to me that because we know that Einstein's equations results from the simplest objective function that you could have, which is the scalar curvature in Riemannian geometry, that's not a great target. I mean, it's great that you can produce something that looks like Einstein's theory out of computational rules. The next one on the list would be Yang-Mills theory. I mean, there are only really four basic equations. Again, the objective function is as simple as it gets. So to Stephen's point, what we know about the current physical world is that 2 out of the 4 equations, fundamental equations for the fields, the things that dance in our world and we call particles or waves, both of those come from the simplest possible curvature equations that one can have in geometry. So if you think of the geometry is largely about curvature, then the 2 simplest structures that can generate equations, called the Yang-Mills Lagrangian or the Yang-Mills Maxwell Lagrangian, which is just you take the size of the curvature and you square it, and that's it. And the other one is you just take a piece of the curvature without squaring it when you have a piece to take, called the scalar curvature, and that's it. The other 2 equations have a slightly different character. I want to leave aside the Higgs field and what would you call the Klein-Gordon equation with the potential. But I would say the next order of business is, do you find the Dirac equation? because it's very difficult to find spinners.
Spinners, yes.
Arising from
computational rules.
Well,
no,
you can do it with you can do.
About it. Yeah, I mean, there's nothing difficult about. So the answer is, do we know how we managed to get spinor representations of the rotation group?
No. Okay. We know how to construct these things.
Yeah.
Okay? There is a mystery about why they are there to construct. Now, there are people who will go to their graves saying, there is no mystery. I know how to construct it. Therefore, I know what it is, which is never true. I mean, we only really understand something in mathematics when we can walk all around it and see it from many different angles. I agree that we know how to construct spinners. I know how to construct Dirac operators, but this is a highly non-trivial question in our world. It comes out of what I call the psychedelic of mathematics, the square root construction, where you ask a question like, what is x squared equals -1? It has no solution in the reals. You have to jump into another space in order to answer the question, right? So it has this different character, which is the answer to the problem isn't found in the space in which the problem was posed. In the case of Einstein's equations and in the Yang-Mills equations, or the souped up version of Maxwell's equations, nonlinear Maxwell theory, if you will, you have something which has a character where I understand where it comes from. In the case of the Dirac equation, you've got much bigger problems. I tried to bring this up on the last live stream, didn't work at all. What do you do in quantum gravity when you don't have an observation of the metric, for example, and therefore you cannot construct the ocean in which the electron is a wave? Now, if you think about it very carefully, in a weird way, electrons are basically functions and photons are basically derivative operators, okay? And bundles,
that's a bizarre way to think about it. I mean,
it's not a bizarre way at all.
You can think about, I mean, I know the mathematical physics, so I understand what you're talking about, but I think it's
then you wouldn't say it's a bizarre way at all, I don't think. In any event, what we're talking about is we're talking about versions of the XY plane and functions and derivatives, right? And the idea of the XY plane, that grows up to become something called fiber bundles, which Stephen mentioned at the beginning. The idea of functions grows up to be something called sections. And the idea of derivatives grows up to be something called connections. Now, these are the basic bread and butter of what goes on before you get to the quantum. And in that picture, there's a big difference between recovering the easiest bits and recovering the hardest bits. So I don't mean to put extra weight on Stephen's shoulders. If he can do the first bits, that's great. But there's a series of challenges that are of escalating difficulty in terms of recovery because of the simplicity of some portions of our model and the Baroque complexity of other portions of the model. For example, the internal quantum number assignments that give the particles their personality, the number of generations, the chirality of the situation. It's very interesting. Stephen's rules are going to have to pick a left or a right. So it's very interesting to how he's going to recover a chiral world. And I just want to...
This is silly. This is silly. You know, let me give you my point of view here, okay? You know, we can talk about details of mathematical physics. It's quite interesting. I know you know a bunch about it. You know, we can go deeply into, you know, how, you know, half integer spin versus integer spin particles work, et cetera, et cetera, et cetera. I mean, what you're doing is you're making the paradigm shift mistake, right? You're talking about things in terms of kind of existing mathematical physics ideas. And yes, you know, you're saying, oh my gosh, you'll never be able to get spinners.
No, I'm not saying
no. I don't think he's saying that.
Let me just make a few points about this.
Yeah, go ahead, Stephen. Yeah.
Okay. I mean, the fact is, we're actually hot on the trail of understanding how fermions versus bosons work. It's quite interesting. It has to do, it seems, with cases where in our, and again, it's sort of a somewhat complicated story, but it's these branch pairs in Branchial space, whether they end up being things that merge after a small number of steps or not, seems to be what is the distinguishing feature between bosons and fermions. How that relates to half integer spin, we don't completely know. It seems to be related to various features of homotopy in the multi-way causal graph. It's quite possible that some of the kinds of mathematical physics that you like a lot are highly relevant in understanding how that homotopy works in the multi-way causal graph. It looks like a limit of the multi-way causal graph is quite possibly related to twistor theory, that one can understand some of the things that happen there on the basis of twistor theory. Whether we can get, we're now understood, we've understood quite a bit about how rotational invariance works, how angular momentum works, but it's kind of a weird business because in a sense, we're trying to build from the machine code up. Yeah. And, we can have a detailed mathematical physics conversation.
But where's the silliness?
That's what most people are interested in here.
Oh, I disagree. I think that people actually want to see whether or not, both of us are saying outlandish things. By the way, I don't think what I was saying was silly at all. So
no, my guess is we've had a miscommunication. Look, it's standard mathematical physics, and I think it's all standard mathematical physics. And the fact is,
I'm going to invoke my referee. I'm going to hold on 1 second. I do want to point something out. I think it's very important. I've heard this from people that I hold in high esteem. Paul Steinhardt was probably Stephen's roommate at Caltech when something like that.
No, it wasn't. I met him once at a conference in 1977 when I was 17 years old.
One reason that Paul says he refuses to ever get a Facebook or Twitter account is because he would invariably be tempted to propose an interesting idea, which by necessity would be new, novel, untested, unproven at some level, and then immediately it would be attacked, assailed, subjugated to constraints and concerns. And I think you guys have both seen that for the following reason, that you both are master explicators of what you do. You both are obviously domain experts in what you know, and you understand the other branches of physics and mathematics that are pertinent to it. However, neither one really knows the other one's, the intimacy of the other one's theories. And I think it's important to realize that just like people assailing your theories from without, I think it's too soon to tell, at least in the case of Stephen's work, which is, in some sense 20 years old or coming up on 20 years old. And in some sense, it's also brand new, because I think when you look at the successful applications, I feel like we should just check those off, Stephen. I mean, biological systems, crystallography, you go down the list, finance, economics, where the Wolfram approach, the new kind of science approach first outlined in 2003, or so, that has already been proven. It doesn't need to be proven. Where I think it's different is where we lay on this extra layer of computability as a fundamental nature of the universe, which from my perception, maybe Stephen, correct me if I'm wrong, has sort of a multiverse component to it. You talk about different aspects of the universe. Well, you talk in an essay that you wrote in 2017 about, the space of all universes, where these rules.
That was before I understood what I now understand.
Yeah. So, but we are barely coming up to where you were in 2017. So can we take a step back? We talked about the paradigm issue. I want to talk a little bit more about how these ideas get into the firmament or get into the zeitgeist.
Yeah, before you do that, I want to just clear something up, because otherwise it'll stick in my craw. Okay. Stephen, I'm not trying to scuttle your theory. I believe that your theory, if you have an approach that works and it's a face up the same mountain, my belief is that you will get to answer these questions. You may tell us for the first time spiritually what a spinor is from a computational perspective. I'm not saying you've only done the easy stuff and the other stuff is really hard. The stuff that you're talking about is really hard. What's going to pick out, the Riemann curvature tensor? However you generate these,
easy.
Great.
That one's fairly easy.
Well, I believe that because it's very natural. There's a reason that in some sense it came first. Before the Wu-Yang dictionary.
I think spinors are going to come out as, the latest thing, which is only a week old, so it's still uncooked, right?
Yes.
Okay, so we're tricking him to sharing this on the live stream.
This is exclusive. This is an exclusive right here.
Well, we probably talked about it on our working session live streams, but the current thought, let me try and explain it. So in quantum mechanics, first point is, in our models, quantum mechanics is a very natural thing. In sort of, when we think about traditional classical mechanics, it's like you throw a ball, it goes in a definite direction. In quantum mechanics, kind of the idea is that the ball, tests out all possible paths, and then we only get to see various probabilities about what happens.
Yeah.
Okay. In our models, there are these things called multi-way systems, which basically are enumerating all the possible paths. And the whole sort of dynamics of how quantum mechanics works comes out of these multi-way systems. Now, what happens is that when you look at one of these multi-way systems at a particular time, you take a slice through it and you get this thing we call branchial space. Branchial space is the analog in the space of quantum states to physical space in kind of ordinary position in the universe.
By physical space, you mean a space like hyperspace?
Yeah, I mean, these branchial surfaces are the analog. They're branch-like hypersurfaces, which are the analog of space-like hypersurfaces in standard space-time. Okay, so this branch-like hypersurface in branchial space, there's an extent in branchial space, which is where as you move through branchial space, you're moving through the space of sort of quantum entanglements. And so states that are further away in branchial space are less quantum entangled than states which are close in branchial space.
What is your notion of a distance?
Well, it's based on, if you look at the multi-way graph, the nearest neighbors in branchial space are things which have a common ancestor one step back in the multi-way graph. So those are what we call branch pairs. I mean, this is, unfortunately, it gets fairly.
No, I appreciate that, but the idea is you have some ordering by number of steps.
A metric, yes.
No, it's a metric-like based on sort of common ancestry in the multi-way graph. And essentially, what happens is that just as there's, oh, look at that, that's a nice
branchial space.
Well, that thing on the left is a multi-way causal graph. The thing on the right is a kind of play version of a kind of mixture of branchial space and physical space. So not probably not the best visualization, but it's something. But anyway, so the idea is so there's physical space that we're all familiar with. There's this branchial space, which is the kind of space of quantum states. Just like there's a speed of light in physical space, in our model, there's a maximum entanglement speed in branchial space, which is kind of the maximum speed at which kind of you can, maximum speed of kind of entanglement in that space. So, okay, why is any of this relevant? Again, this is, I'm in the Einstein equations, which have to do with physical space. One is looking at, one way to view the Einstein equations is to think about what happens to a geodesic, what happens to the path of a particle in space-time. And what essentially what's happening in the Einstein equations is that energy momentum causes deflections in geodesics in space-time. In branchial space, the exact same thing happens. Essentially, energy momentum causes deflections in geodesics in branchial space. And it turns out that deflection process gives one the Feynman path integral, which is really cool. And it's one of the things that I sort of found the most elegant in the things that we've done so far in this theory, that what in physical space is the Einstein equations, in branchial space is the path integral. Okay, why is this relevant to fermions and bosons? The reason it's relevant is that
wait, I just want to take a moment to think about what you just said. You said that something in general relativity, that is Einstein's equations, which are maximally resistant of all of our structures to quantization, is analogous in some ways to the Feynman path integral, which I'm going to disagree later with your characterization, which is Feynman's sort of characterization, the linguistic description of what we claim is happening when we're taking one of these integrals. But the point is that you're just making a claim en passant, which is astounding to begin with, so if true, right? Which is that the Einstein equations are somehow intimately bound up in the quintessential centerpiece of quantum field theory, not even quantum mechanics. Right.
That they are the Einstein equations. I mean, this is a remarkable thing, which I certainly did not see coming. That the path integral is the exact same thing as the Einstein equations, but in a different kind of space.
Never heard this.
Right. So that's one of the things that we discovered, like, I don't know, 6-7 months ago. That was like, wow. And those two things meet up when you think about black holes and black hole information and so on. There's sort of this, and in fact, the ADS-CFT correspondence is almost certainly taking this multi-way causal graph and projecting it into space-time and projecting it into Branchial space. That it's the same graph projected in two different ways, corresponds to the kind of general relativity ADS side of ADS-CFT and the quantum field theory CFT side of it. That's almost certainly what that is, and various people are working on filling in the details of that. So it's pretty neat. So then, okay, you asked about fermions and bosons, and I was going to tell you this week's kind of way of getting to that. And these are complicated things, so it takes a few steps.
Yeah.
Okay, so the next thing to realize is in quantum mechanics, one of the things that emerged, particularly from von Neumann's work, was this idea of, there is an amplitude, it is a complex number, it, operates in Hilbert space, et cetera, et cetera, et cetera. One of the things that was implicitly done was something which I think turns out to be a mistake, which is that the magnitude and the phase of these quantum amplitudes were sort of all packaged together.
You mean the projectivization of a Hilbert space?
Yes. I mean, the fact that you can think about it as a magnitude and phase is just a complex number. What in our models, what ends up happening is the magnitude and the phase come from completely different places. And so what happens is the magnitude has to do with the counting of paths going through this multi-way graph. The phase has to do with essentially where you land up in Branchial space. And actually, one of the things that we figured out about a week or two ago is it's just unbelievably easy to get the double slit experiment to work. And we get nice pictures.
I don't know what that means, but the first point, if I understand.
Interference in quantum mechanics, right?
Well, I understand that.
Right.
That's not what, okay, go ahead.
You mean you don't understand how it's easy, it comes out naturally in some sense?
No, what he's saying, I mean, we have to go back and unpack what the good doctor is saying. He is talking about the fact that we claim that we work in a Hilbert space. We don't work in a Hilbert space. We work in something called the projectivization of a Hilbert space. And effectively, that destroys a certain amount of structure. So we begin with something like a vector space. We remove the origin. We pluck it out like the seed out of a cherry. Yeah, and then we take, all of the sort of meat and we compress it in this particular way. And what Stephen is saying is that is a loss of information that we teach physicists with their mother's milk, and that this may be, in fact, throwing away information that is actually experimentally much more important.
More or less. I mean, I think that let's not go off into projective Hilbert space for a minute. You
guys never take me anywhere.
Fly me to the Hilbert space.
Right. The thing that ends up being interesting is when you think about kind of these again, this is the kind of these sort of quantum geodesics. What ends up happening is the phase of the quantum amplitude is essentially defined by its position in Branchial space. So you think about these in general relativity, you'd think about, a geodesic is deflected by the presence of mass. It's attracted to some massive object, moves around it. It changes the direction of the geodesic is changed by the presence of mass. Okay, in Branchial space, it's the same story. The geodesic is deflected by the presence of energy momentum. That presence of energy momentum corresponds to the Lagrangian in quantum field theory. And what one is doing is deflecting that geodesic. The deflection of the geodesic, the interpretation of that is it's changing the phase of the quantum amplitude. It's changing where that geodesic is going to land in Branchial space, which changes the phase of the quantum amplitude. And amusingly enough, what appears in the Feynman path integral is exactly e to the I over h bar times the action integral. The action integral is the integral in our world of the divergence of causal edges, which corresponds to the Lagrangian.
Okay, so there seem to be multiple things going on here. If I can just,
I do want to invoke my my privilege here, being the moderator. We've covered the first of our 6 or 7 topics in an hour and 15 minutes. It's clear to me.
I just want to finish on bosons for a second.
Okay, please finish on bosons, and let's move to our next, which will be experimental testability.
The flavor of this is that what ends up happening with bosons is this kind of collection in branchial space, this kind of focusing in branchial space. And what seems to happen with fermions is a divergence in branchial space. And it's, one of the things that I've always been curious about is why are there only fermions and bosons? Why isn't there lots of, intermediate parastatistics and so on? And I think that the answer is that it's going to end up being the case that basically in branchial space, things either diverge or they don't diverge. And that's going to, but there's much mathematical physics packing that has to go around this.
And if I could just take 15 seconds to riff off this.
Okay.
You have a situation in which the great thing about general relativity, for example, is that all you need is length and angle. And length and angle turns out to amount to a derivative operator, which turns out to have mixed partials that don't commute. You can measure their failure. That's the curvature. You knock it down with linear algebra and you create gravity. It's a miracle. It's fantastic. On the other hand, it's not that surprising that if you have a situation in which you have some notion of like size and perpendicularity, that you can create something like that. For example, you do have something called Mahalanobis distance that you can get out of data. You can treat a covariance matrix like a Riemannian metric, if you will. So there are all sorts of ways in which we already know that that anything that leads to length and angle becomes geometric. And I think that, that's both very good for Dr. Wolfram, and it is also just a bit of caution for the rest of us that on the early part may lead you on because it's a different way of describing length and angle and the consequences, which thanks to both Einstein, Grossman, and I guess Hilbert, we know that all we're looking for in some sense is the most basic consequence of that. It'll be cool to see it come out. And I do believe that you may likely get fermions out of a question. You may have to ask the question about how to take the square root of something. I'll be astounded if you have fermions without taking a square root. But the key feature, is that you're not that far away from geometry as soon as you're talking about Mahalanobis distance and covariance matrix and data.
Okay, so the one cool thing is that the uncertainty principle in our theory is basically the analog of Riemann curvature in branchial space. So the non-commuting of variables is just like the non-commuting.
And in geometric quantization, it is literally the curvature tensor in the Hamiltonian picture.
Absolutely.
Right. So,
by the way, in terms of the square root thing, I have the following guess. Okay, that what basically happens in branchial space is you have these branch pairs and they converge. Okay, branch pairs, next step, they converge. I think that the boson case is they diverge and they converge. The fermion case is they diverge and they don't converge. And so in some sense, the square root is being taken by the fact that you're having the beginning of that diamond, but not the end of the diamond.
Sounds like the difference between commutators and anti-commutators.
Yeah, it's my first guess about how that works. And the thing that, again, I thought we were going to have to, find actual electrons to be able to distinguish fermions and bosons. It's seeming increasingly likely that we can basically understand fermions in bulk without having to know exactly how particles work.
By the way, let me kick it over to you, Brian. I'll save my comments for this. They'll fit in somewhere.
Okay. What I want to do now is sort of compare and contrast different approaches, not necessarily only from the two of you, but in the context that I often get. Well, first of all, the common thing that I get from all my friends on Reddit or wherever else this gets posted is how come these things aren't being peer reviewed and what kinds of falsifiable predictions are they making? Let's start with the latter. Stephen, you and I talked back in April. And you made it clear that things such as the fundamental constants of nature, the speed of light, are emergent or are embedded, encoded, encrypted within your new findings. I want to know, are there new predictions that could be used instead of retrodictions? Not that they don't have validity, not that they don't have a value. After all, Einstein, in some sense validated his theory on a retrodiction, which was known for millions of years. It was known for years, the perihelion advance of the planet Mercury, and it had to be reconciled with Einstein's predictions, and through observations, it was found to be true. I want to know, Stephen, are there new fundamental predictions that you can point to that have, at least in principle, a chance of being detected? And then I'll have a similar question for Eric.
Well, let's see. I don't do the dueling theories theory, but
no, I'm not gonna. Yeah, I'm not gonna duel with that.
It's some. The thing that okay, falsifiability is a weird concept that has all kinds of problems. But the fact is, first thing is, the number one thing that we're building is a framework, like calculus. Calculus is not something that's falsifiable. Calculus is a framework for doing things. Second question is, does calculus usefully apply to the universe? That's something we can validly ask. And that's something that we can, there are things which are sort of generic predictions from the framework. So the thing we're trying to do right now is what people should do when they first introduce some, new set of ideas, which is, can we actually reproduce, can we make theoretical predictions?
Absolutely.
Can we reproduce what has been known before? And can we get out vastly more than we put in?
Yes.
We put very little in. And the question is, do we get all these things out, or do we have to add some special kludge to get fermions? Or do fermions come out naturally as soon as we understand how to get there? And the thing which has been remarkable so far is, we've been checking off, do we get this? Do we get that? Do we get that? So far, touch wood, no kludges. I mean, so far, it's been hard work, but nothing has been like, oh my gosh, the universe, the theory predicts the universe should be 26-dimensional. We have to explain why it's not, type thing. We haven't had any of those kind of, kludge barriers, so to speak. So that's encouraging. Now, in terms of actually making specific measurable predictions, a couple of issues. First issue is going from the raw theory, the low-level machine code, to something where you turn a telescope in that direction and you see a particular thing. There's lots of hard work and lots of astrophysics and so on to be done in going from one place to another. That's the first point. The second point is that to actually make, one of the things in our theory is there is one scale. Same happened with Einstein's theory, actually, although for various reasons, we can talk about that. But there's one scale, which is this maximum entanglement speed. We don't know what the value of that is. We have some guesses, but we don't know its value. If we knew its value, we would have a whole bunch of predictions immediately, but we don't know its value. Einstein had the same problem. He had the cosmological constant. He didn't know its value. It's a lot of predictions he might have liked to make, he couldn't make because he didn't know the value of the cosmological constant. He had one meta prediction was that the universe wasn't expanding, he thought, which is why he added his cosmological constant in the first place. But that's his scale. So then he had a few scale-independent predictions. In particular, the bending of light around the sun being a factor of 2 larger than had been predicted in the previous theory, things like that. So one thing that we've been interested in is what scale-independent predictions can we make? That's question one. And question two, what predictions can we make that are, as soon as we know this one scale, we immediately have predictions. And then which predictions can we make that have the shortest distance in terms of the tower of astrophysics or particle physics or whatever that have to be done? It's a cautionary tale that, like Newton, for example, he goes through his whole Principia, and he works out lots of things about his law of gravity. And he has a section about the moon, and the section about the moon ends with the sentence, I think, but the apse of the moon is twice as great. Right. In other words, he got the wrong answer. And, one might have said, oh my gosh, he got the wrong answer. He better abandon the whole theory and run away, so to speak. Turns out it was just hard to do those calculations. It took another 150 years to get them nailed down. So that wasn't, so one has to be a little bit, and Einstein also, the first time he computed the bending of light around the sun, he got it wrong. Yep. And it was, fortunate the first, experiment that was going to be done on that didn't end up getting done because of World War I. And so, by the time an experiment did get done, he'd managed to get the right answer. Whether the experiment was right is a different story, but that's another thing. But I think that so the question of, do we have kind of scale independent predictions? The answer is quite possibly. I think there's one quite likely one that has to do with two photon correlations for photons in orbit around rotating black holes. Which is a slightly obscure thing, but it's not completely out of the range of what's experimentally accessible. It's kind of amusing that that's so bizarrely similar. It's a kind of a quantum analog of Einstein's, bending of light around the sun type thing. But that's one kind of thing. Another thing is a suggestion, at least from the theory, about the existence of particles much lighter than the electron, maybe 10 to the 20th times lighter than the electron. That number depends on the scale parameter that we don't know. The existence of such particles probably has a bunch of implications for dark matter, which are things that we're planning to work out. There are a bunch of implications for cosmology. There's an expectation, not a necessary feature, but a suggestion, at least from the model, that the universe starts kind of infinite dimensional and only gradually kind of decayed down to the sort of modest 3 dimensions that we have now. That has a bunch of implications for inflationary scenarios for the universe and so on. I think the most outlandish possibility, which I don't think will actually happen, is that that still at the time of recombination, when your cosmic microwave background globe was minted, so to speak, that it would still be that there would still be a trace of some of the early discrete processes that happened in the very early stages of the universe. I really doubt that it would have survived that long, but if it did, the absolutely outlandish possibility is that the rule for the universe might be painted in the microwave background radiation, which would be truly
right
remarkable.
up my alley,
I don't think that would happen. I think it's very unlikely. But early density perturbations, there might be some things that would be a result of this changing dimensional scenario that's rather different from the traditional exponential expansion in 4-dimensional space-time of inflationary cosmology. That's on the one side. On the particle physics side, one of the things is that it's looking very much as if quantum computing at some fundamental level can't work. However, seeing that and seeing the actual effects of our theory for decoherence and things like that, it's not at all clear that the can't work point is something experimentally accessible. I think that it's a question, is there some clever experiment that can be done in quantum computing that could see this maximum entanglement speed? That's basically and we don't know what the value of that speed is, so we can't really tell.
Right.
One estimate that we have of that speed is 10 to the 5 solar masses per second. If that estimate is correct, then it is possible that in black hole, it's possible there will be a small effect in a black hole merger of 1.5 solar mass type size would have a bigger effect if two sort of central black holes of two galaxies happen to collide and merge. Then there would be a bigger effect. It's also conceivable that there might be an effect when black holes initially form. And this is an astrophysics question for you, Brian. How long does it take a black hole to actually form? Once you have infalling matter, the question is whether in 10 to the minus 5 seconds, whether one can tell what's happening in the last 10 to the minus 5 seconds of the formation of a black hole. If one can, and if our estimate of the maximum entanglement speed is right, then there will probably be differences from the predictions of general relativity for that case.
Yeah, this is a big question. Primordial black hole formation, the end of inflation. These are really important questions that, it's good to hear, especially that you're, providing potential full employment for my graduate students down the line.
Yes, there will be lots of work to do in figuring out the consequences of these things. It's particularly when we get this kind of way of actually doing computations in general relativity from our model set up as a piece of practical numerical relativity. And that will probably happen fairly quickly. And we'll actually be able to see a bunch of these effects directly in the computations that we do, but there'll be, just layers of astrophysics to do in actually comparing with things.
And Eric, I want you to sort of opine on this provocative question that I'm being asked in the chat room. And that is, what value is a theory if it is not to be testable? That which can be claimed without evidence can be dismissed without evidence, as our friend Christopher Hitchens used to say, I believe. So in the context of geometric unity, I'm not asking you to talk about somebody else's book, but talk your own book for a second. Are there things that are testable by graduate students in my group or other brilliant students around the world? Are there predictions? Are there retrodictions that are crisp enough to satisfy Popper, A? And do you think we should continue to feed Popper? Has he had enough Popper corn?
All right. So the first point would be there's a missing layer between you and myself. What we do typically, Stephen notwithstanding, is that we come up with a classical model in the form of some sort of geometry. Hopefully it quantizes itself or something like geometric quantization. And then we try to figure out what the testable consequences are at any given energy level through a bunch of phenomenologists, experimentalists, and pure quantum field theorists working hand in hand in our harmonious fashion. At least that's the theory. So given that we have a missing layer, there's tons I can say about what's new, what's different, and what my theory says, and effectively what would make it wrong. So I'm happy to get into that because it effectively says that a lot of our standard verbiage around what we found is in fact wrong. So for example, standard thing is the world is chiral. The weak force sees the difference between our left hand and our right hand, spiritually speaking. My claim is that the world is not fundamentally chiral. It is emergently chiral, and that in fact it begins in a non-chiral fashion, which solves the problem that Sabina does not see, which is what chooses whether it's going to be the left half or the right half, effectively, that makes up us in some sense.
So don't we already know from neutrino masses that we're not seeing a completely chiral situation?
Well, we can get into the issue of how to interpret the neutrino masses. My claim would be that we have entire sectors that we're not seeing. So for example, unadorned spin 1/2 bundles that would be tensored with, if you will, the conjugate of a 16-dimensional representation, which imparts the particles their personalities. So that is not something that's seen. And I've analogized it for those of you watching at home rather than listening, where you have a hand and you see with 3 fingers in the middle that you think there's a symmetry in the hand. And then you have this problem about how do I make my pinky look like my thumb? And you don't realize that there's an entire other hand and that it's thumb to thumb and pinky to pinky, not pinky to thumb. It's the symmetry. So there is a non-chiral world that is emergently chiral, which is fooling us into thinking it's fundamentally chiral. There are only 2 generations, not 3 generations. People will immediately say, well, how do you explain the fact that we've seen the tau particle in the top and bottom quarks? And the claim is that is not a generation because it will not unify as you heat the soup up in the same way as the first 2 generations will unify. In fact, it will unify with another collection of particles, also spin 1/2, which I believe, if I recall correctly, the thing that will be misinterpreted as an internal representation, I think will be like 112 dimensional rather than 16. There will be no internal representations.
One of the fun...
Wait, let me just get through it. There will be no internal symmetries. This has been a huge trip up for things like supersymmetry, where we keep looking for these super partners, which I've analogized a little bit to what happens if you're convinced that Spider-Man should be, in fact, Clark Kent, should be accompanied by Clark Kent, and Peter Parker should be accompanied by Superman. We have this wrong. There is no internal symmetry, nor should you expect internal symmetry, because this comes out of 2 fundamental origin stories. One for the space-time manifold, another for effectively the y-axis above that as the x-axis. So we decide that somehow we have space-time in Einstein, and then somehow we get this thing called SU3 cross SU2 cross U1 that falls out of the sky. which is a second origin story. There is not two origin stories, there is one. Einstein, I believe, one of the problems, Stephen, I'm going to say, is that we have been in a very difficult position relative to Einstein, because unlike anyone else, because of the thought experiments, we have a reverence for not only what he gave us in terms of equations, but how he thought, and the beautiful humanity that he imparted to everyone. So we don't want to harm him in any way. It's also the fact that he was wrong, and he was wrong in an interesting way, in the same way I believe that Newton was wrong, and we souped up Newton with Einstein, but that physics is taking place, in my opinion, on two separate spaces. And you can call X and Y, or Brian, I've joked with you calling it Haaretz and Hashemayim, the heaven and the earth. In these two spaces, there is a map between. And that is the map that, in fact, Einstein started playing with, but he did not think to pull back the information from space 2 onto space 1, from space X to space Y. I believe that there is a deformation complex, which in Euclidean signature is elliptic, which in fact tells us why the self-dual equations and the Chern-Simons gauge theory that were studied in the late 70s, early 80s, are so important. In fact, it was a special example of a much more general structure that comes out of geometric unity. That there is not two kinds of geometry in this situation. One Riemannian geometry underlying general relativity, and Arrhenius geometry of fiber bundles underlying the standard model. There is in fact one geometry. And that one geometry is why it's called geometric unity, and it has to do with the difficulty of a lie that we tell in general relativity, which is that we say that it is a so-called gauge theory, where we try to get the gauge group to be something called the diffeomorphism group, or general coordinate invariance. We allow it to act on the space of metrics, whereas in the case of the standard model, we have a space not of metrics, but of derivative operators from calculus called connections. And the group we have is the gauge group. And the gauge group is an infinite dimensional beast that acts on the space of connection. We do not understand, in fact, that telling this lie to make general relativity look like a gauge theory, in fact, block progress, and that we should treat it as an honest gauge theory. We are going to have to recognize that the cosmological constant is not constant. It is a field which acquires a VEV, or a vacuum expectation value, as it is lured away by topological mechanisms. We are going to see that we got the Lorentz group wrong. We focused on the Lorentz group when we meant to be focusing on the gauge group. We formed its inhomogeneous extension, called it the Poincaré group. In fact, you're supposed to extend it by something called add-valued one forms to create effectively the inhomogeneous gauge group. That is the object on which you're supposed to do supersymmetric analysis. And so our concept of supersymmetry is wrong. In effect, we're acting on the wrong group. We've chosen Minkowski space as the naturally occurring affine space. It is not the right place to be playing. The right place to be playing is the space of connections. There's a huge number of things I can tell you about the missing matter. What in our sector, it's SU3 cross SU2 cross U1 internal quantum numbers will be. So that's, 16 new particles that are spin 3/2 with conjugate internal quantum numbers. So the same thing as our usual 16-dimensional representation, but the complex conjugate thereof, which we have not seen yet, and explaining why the illusion of 3 generations is generated by what would be called branching rules with respect to Lie algebra and Lie group representation decomposition. So yes, I can tell you a bunch of new particles. I can tell you about non-chirality, the number of generations, how Einstein is wrong, what spaces we're supposed to be doing this on. And then there's the question about, okay, well, what can you tell us about the accelerators? And by the way, this is all subject to if my theory is correct, but it gets boring to say if my theory is correct over and over again. So there should just be a general caveat that all of this assumes general geometric unity is in fact correct. Mm-hmm. So yes, there's a ton of specificity, and Brian, I'm looking forward to coming down to UCSD and and actually doing it. But let me just say something. Yeah, I've been very pissed off about this claim that what I'm talking about, different from what Dr. Wolfram is talking about, is so impenetrable and difficult. It isn't. And it really has to do with the sickness in our field, that our field just isn't interested in some sense because it doesn't believe. We all know that the problems have gotten so difficult and so hard, and so many smart people have been over them, that a sense of learned helplessness has invaded the field, which we have to talk about.
But wait, my friend, hold on.
Wait.
All right.
A sense of learned helplessness has invaded the field. People no longer feel like they're actual physicists that can connect to Schrodinger or Heisenberg or Dirac or Einstein or Planck. People don't even feel like Weinberg and Yang, who are still with us, are in some sense, nobody's gone to, I see losing the Nobel Prize over Brian's shoulder. Nobody's gone to Stockholm for advances in fundamental physical theory since the theories put forward since the early 1970s. I think that's a correct statement. So all the people who've contributed to the fundamental canon are either dead or septuagenarians or higher, I think. Maybe Frank Wilczek was born in 1951, is at the end of his 60s. We have to recognize that this sense that it is impossible has caused lots of us to start faking it and to start calculating what we need to do for our careers rather than how to actually advance the science, which is one reason that both Stephen and I are viewed as incredibly brash, effectively too brusque, maybe too arrogant. And the answer, I believe, is that we have to drive this field out of its sense that it's playing at physics rather than doing physics. It's talking around physics. And one of the things I want to do on these live streams is I want to actually talk about the meat of the theories and let people scurry to Wikipedia or help each other out to try to understand what is said rather than make it an enjoyable product for everyone.
I agree. But Stephen has said earlier, this is simple. Okay, it's not easy. It's not trivial. My 9-year-old, who you'll meet someday, hopefully both of you guys, he can play around with Rule 30. He can get stimulated. He can engage with it. So when you say, that it's not difficult, I don't agree that there's a character class that differentiates, and I'm not pitting it one against another. For certain, there are more complicated models than even Eric's, in my opinion.
Wait, how is my model complicated?
I'm just a simple experimentalist. 14-dimensional, dual spaces, and look, if it's too complicated for Sabina to understand, I think our general.
Wait. This is just unfair, and I want to be very clear about it. If you talk about general relativity, which Stephen has been talking about throughout our live stream, he's talking about the idea that you have a space, call it X, and it has a metric on it. And that metric is a map into the space of all possible metrics, call that Y. That X and that Y are where geometric unity lives. So with all due respect to Sabina and her, I can't understand anything, it's all so complicated. Cut the crap. You've got a map between a proto-space-time and a space of metrics, and that Riemannian metric is simply a map between two topological spaces. It's not that complicated. Brian, it's just not true.
Okay. Let's move on. Actually, I want
to make a few comments about
Okay, Stephen, go ahead.
So maybe people will find interesting. I mean, maps between topological spaces, diffeomorphisms, these kinds of ideas, right? I happened to learn these ideas when I was a kid. Most people don't. Mm-hmm. These are fairly, most people learn those ideas in, mid, math college, if they go to a fancy college, maybe math graduate school, those kinds of things. They happen to be fairly complicated. Mm-hmm. There are fields of science where people can contribute without having gone to graduate school. There are other fields where they can't contribute very much. Mm-hmm. We see that in, people, one of the great things about kind of some of these computational areas of science is that because it's kind of, because it's very new territory, it's possible for people to contribute without having kind of gone to graduate school and learned a whole big stack of concepts. Mm-hmm. One of the things, I get pretty much every day, a theory of physics from somebody. Mm-hmm. Eric's version is, he went to Harvard and got a PhD in mathematical physics. So his version is much better dressed than most of the versions that I see, okay? And most of the versions that I see are, I find it disappointing because it feels like people are, writing poetry that nobody's going to read, and they're doing it using kind of high school level physics knowledge.
It's mostly cranks.
Yeah.
Well,
People who may be well-meaning, but they don't realize that they're way out of their depth.
Yeah, right. But the main thing is that they don't know what got done in the 20th century in physics.
Yeah.
And what got done in the 20th century in physics requires kind of graduate school level knowledge to understand. And we can say it isn't true, but it is true. I mean, it's, general relativity and quantum field theory, Eric may say they're simple theories. I think they're kind of simple theories, but that's because I learned about them when I was, 12, 13 years old. Mm-hmm. And by now they seem like simple theories.
And if it's simple to you, or if it's even marginally complex to Stephen, what help?
Well, but also just the whole language of talking about things, this is kind of math graduate school type language. And that's, now, is there a way to state these things about fiber bundles and so on without sort of super fancy language? Quite possibly. Maybe some of the things we're trying to do will give a way to do that.
Yeah, and it's part of the hope of just bringing your communities together. Let me move on just because we don't have much time. You guys are very gracious with your time. I want to respect it, and I have kids to put to bed. But I do want to ask the following question that my audience is asking. When we think about the power of these different approaches, let's take a step away from either one of yours. There's been a lot made about artificial intelligence and the prospects for, as Max Tegmark has put it, an artificial physicist, an artificial Galileo. What role do you guys see artificial intelligence playing? And then where I'm going next. I know that you guys know I'm going to the simulation hypothesis, and I've talked to you guys individually, maybe offline about this, but the audience is very keen to know, your two esteemed gentlemen, what you think about the prospects for AI and as a benefit to physics. And then later we'll ask about the simulation hypothesis. Let me start with Stephen, please.
I mean, I've worked on what is now called AI for about 40 something years. So I know a tiny bit about it.
Yes.
A lot of, I don't know where to start. I mean, if you're talking about machine learning, if you're talking about, let's sort of throw everything we know about physics into a machine learning system and see whether it can figure out the laws of physics.
That's one level. Yeah, that's one level. Noam Chomsky was on my show and said, he's sanguine about what you just described, perhaps, as is Max Tegmark, but the true creative stroke, he has no, the kind of insight.
The question is, what is, it's a little bit complicated because in, computational irreducibility tells us that we can know the rules for something, but have no way to kind of have a large scale narrative for how the thing happens. So in other words, we might say, yes, we've succeeded. We found rules that reproduce physics. Mm-hmm. You say, well, tell me how they work. You say, well, here are the rules. But you say, well, tell me a story about how they work. Tell me a high level, version of how they work. That may not be possible. I mean, for example, in linguistics, picking on Noam Chomsky's area, and I talked to him about this. I mean, we may have a description of how brains work and how brains process language at a sort of microscopic computational level, and we may still, and it may be completely accurate, and we may still not have anything we would call a satisfactory science of linguistics. Mm-hmm. So, in other words, it's a slightly complicated thing, and the question of whether we can get a current machine learning system to reverse engineer the laws of physics. To some extent, you can do that. To a fantastic extent of figuring out everything, you won't be able to do that, I don't think. And the challenge, again, we keep on coming at things at really weird angles. But there's okay, the way I see it, there's kind of what's possible in the computational universe, what simple programs can do. There's this kind of ocean of computational possibility. There's what we humans understand. That's another kind of piece. And there's also what the physical universe does. And I've spent a large part of my life trying to bridge between the sort of ocean of computational possibility and what we humans understand. That's the whole sort of point of the computational language I've built, is to have a way to have humans be able to think about things computationally and be able to communicate what they want in a computational fashion. Now we have this sort of third piece of physics, and the question is how we describe, how we make this bridge between sort of the physical universe doing what it does, our ability to tell a narrative about what's going on, and this kind of computation in the middle as this kind of mediator of those two things. But I mean, it's a mess. I would say that I mean, this is a longer discussion, and I think this is probably the wrong angle to come at it with. If you say, are we going to have a magic thing that we can throw stuff into and get out the theory of physics? Well, I doubt it. You talked about the simulation argument. I always find it kind of charming that people say, I'm an atheist. I believe in science. What I believe is that we're in this universe, and this universe is actually a simulation operated by
a deity
beyond the universe. It's like, but I'm an atheist.
Exactly, right. And then all the morality that entails therein. Yes, go ahead.
Right, but I think that more seriously, I think that sort of argument is kind of philosophically doomed, because by the time you have definite laws for physics, there isn't much for the God to do, so to speak.
Mm-hmm.
Now, the only thing you might say is, but the God gets to pick the laws of physics, except that we now seem to have found that it actually doesn't matter what the laws of physics are. Mm-hmm. That in some sense, in this kind of, again, for reasons that, again, this is a slightly longer story, but what matters is that we are observing physics in a certain way, and that's what gives us the laws that we believe to be laws of physics. And there really isn't, in a sense, there's nothing for the God to do other than to decide that our universe is going to be computational, not hypercomputational, not below computational. And even if those other sort of kind of conceptual universes exist, again, it's a matter of science to be able to say that we simply can't communicate with them. They're just not things which are in any way connected to what we can perceive. So I think I don't know. I do like the idea, though, that there's a connection between sort of AI physics and the simulation argument. I think that's an interesting and bizarre connection, which I think would be fun to unpack some more.
Mm-hmm. And Eric, you want to opine on this, or would you? Yeah, go ahead.
I don't really know whether it even requires AI and or AGI. There's a particular kind of move that we haven't programmed into computers yet, so far as I'm aware. Now, Stephen probably knows this much better than I do, but there's a weird move that comes up over and over again, which has to do with reaching for something outside of your model and knowing what to reach for. So, for example, you have a problem with the weak interactions that a neutron, when it decays into a proton and an electron called beta decay, doesn't seem to have enough energy in the final products to conserve energy from the initial products. So Pauli had to...
Oh, yeah. Okay. You're explaining how neutrinos come to be. Yeah, okay, fine. Yes.
Right, because it's like one of the most important stories we have. Not everybody knows it. You have a problem that you've got three lines coming into a point, and there's a failure of conservation of momentum. And so you have to hypothesize a fourth line. You had a different problem when Dirac came out with his theory, which is that he only had the electron and the proton. They were oppositely charged. So he decided that one was the antiparticle of the other. Instead, this is the part, similar to the Peter Parker Clark Kent issue, he should have hypothesized a positron to be the anti-electron, and an antiproton to be the antiparticle of the familiar proton. That move was too much, and in fact, Heisenberg chastised him. There's an issue about understanding how spin comes about. So effectively, when I've said that the square root is the psychedelic of mathematics, you have to give your computer program psychedelics effectively so that it can invent new stuff. That is, I can adjoin something called I or ij and k to solve a problem that was posed in the real numbers, and then I get the quaternions or the complex numbers or even the octonions. I'm going to augment my theory of something called differential forms to something called the theory of spinors. Can you discover something called the Pfaffian, which is the square root of the determinant for a particular class of matrices? Can you discover that the Euler class is, in a certain sense, the square root of something called the Pontryagin class? All of these things are these non-trivial moves where something that is not present in the initial formulation is guessable as the thing that would be needed to complete the stuff that we can see with stuff that we can't to get a consistent system. If you can teach a computer about primitives and give it the ability to guess outside of the system that you've taught it so that it can self-adjoin, and I don't see any impediment to this currently, you would have a system that would be potent enough to explore not only the theory that you feed it, but the theories that it can build from that theory. In essence, the computer program is being asked to do something similar than what we're asking theoretical physics to do. Again, everybody complains about how complicated this is, and I'm sick and tired and bored of hearing it. Stephen's correct. You do have to learn some level of mathematics. Typically, this would be somewhat like learning the French language before exploring French literature. Yeah, it's expensive. If you want to learn a foreign language, it costs money and time. Same thing for learning differential geometry and quantum field theory. The situation that we're facing is that your computer program has to be capable of building larger worlds by adjoining things that would make puzzles in the worlds that it knows about make sense. And that process of inferential guessing outside of anything that's been taught is a different problem than the problem of finding, let's say, chess moves or Go moves by being able to search a larger space where the search space is implicit in the rules. So do I believe that it requires AGI? No, one of the stories that I don't think we talk that much about is how much we thought AGI or artificial general intelligence would be needed to do all sorts of things. And the great surprise is we don't need anything like artificial general intelligence to do most of the things that supposedly intelligent systems now do. We thought that AGI and our consciousness and our intelligence was necessary. It turns out that much less is usually necessary. It is entirely possible that we don't need to wait around and we can have the computers guess it. And to the issue of atheism and the simulators and the simulated, we have two separate stories. One story in which we are going to build the intelligence, the AGI fear, which is it's going to be smarter than us. We have another one in which we are the simulated, and there's the simulator somewhere else. If you put the two stories together, you see that in a weird way, God should be scared about us becoming intelligent when we finally learn what our source code is. This is the moment where Skynet becomes self-aware, and the thing that nobody sees coming is that we are the AI. We are the AGI that emerged in somebody else's system. And whether or not that somebody else was sentient or not is a different question. But Einstein asked this thing, he said, I don't care about the spectrum or this or that element. What really bothers me is whether or not the creator had any choice, or what interests me is whether the creator had any choice in the way the world was made. This is an interesting concept of not being all powerful, but being all constrained. And perhaps the creator's sole function, if you will, is to turn on the lights. And everything else follows from that. This is sort of a Leibnizian monad construction where the idea is that the rules effectively tell us what is going to happen and there's very little room for anything else. But I think that part of the reason that we keep asking these questions is, to be blunt, pessimism. Rather than working on the actually hard stuff, either in Stephen's case of trying to do it through computation, or my case, trying to remain within the standard mathematical toolkit, people are so frustrated that we waste our lives talking about the mathematical universe hypothesis, the simulation hypothesis. We do all sorts of nonsensical work on theories that have nothing to do with physical reality. And I just think it would be better if we stopped wasting our time talking around physics and started talking about physics itself.
Great. Well, guys, I have to go. You guys have been so generous with your time. You've answered a lot of the questions that the audience had, and for that, I'm very thankful from both coasts. Any final words, Stephen?
Well, I did think there was going to be one question you wanted to ask us about peer review and our attitudes towards it, which I think people are going to want to know.
I think we should wrap it up. Maybe we'll take that up on a future podcast with you guys individually. The time has really come to go, or I'll be in a lot of trouble with a multiverse of children screaming at me. Stephen, anything you'd like to leave the audience with? Any way that they can engage and perhaps participate in the exciting work of Wolfram Research?
I don't know. You can use use Wolfram language, use Wolfram Alpha. You can come to live streams we do frequently about the physics project. You can look at the physics website. You'll find all of the programs and things there. It seems like people are finding this stuff, so which is great.
That is good.
Yeah.
And we'll put a link to the channel, the YouTube channel, where folks can find your many, many live streams and presentations as well. Eric, something for closeout, where can people find you and engage with you?
I would say come find us at the portal. I think there's also an Eric Weinstein, ericweinstein.org. Look for the geometric unity presentation, which was a special presentation within the portal series. I am looking forward to hosting Stephen, getting into the thick of his theory and how it works. I think that one of the things that people should get engaged with is both why people are so pessimistic and negative about every new emergence. You should learn about the no-go theorems and all of the things that a theory would have to fit.
I don't think people are particularly negative. I mean, honestly, we've been playing up the negativism, but honestly, what I'm seeing is people being very enthusiastic about what we're doing. So far, I haven't seen anybody, I'd be interested to hear from somebody credible who says, I mean, you've said, I don't believe your theory. So you're—
Wait a second. No, I believe that your theory is either going to reproduce a lot of what it is that we already know and then tell us something new potentially. I'm not disagreeing with it. I've said that it may be a face up to some common summit. It's certainly not the face that I'm taking, but I don't think that's character. We should hash that out when we do each other's podcasts. The issue that I wanted to get to, though, is, yeah, there is a lot of negativity. You can read about it in the Reddit comments. You can read about it very often left in the YouTube comments. Some people in the field are very disgruntled. Very few people have wanted to say, I've waded in, I've tried to look at it, I've really come to understand it, and I still think these guys are talking crap. I think Stephen's exactly right, that the coincidence of his work and my work being on the same show, I don't see any need to fit them together. And I think that
not at all.
And I think that if they're both right, then they would have to be fit together. And most probably, of course, they're both wrong, because that we have to say these words. With that said, get excited about people who are trying to find ways out of the learned helplessness that comes out of the no-go theorems, the pessimism that came out of the LHC. I disagree with Stephen. I still think that there is a core community that's angry that people outside are speaking to the world through this.
They may be angry about you. I don't think they're very angry about me. At least not there. Yeah. Maybe they were.
There is pessimism. I think Eric's talking specifically.
I mean, I think that—
I guarantee you there are people angry about you too, Stephen. It's not just about me. It's in general that we're all up against a question where nobody has any precedent.
I think people have— one thing that I think is the case is that it's what I've noticed, for example, about peer review, which we're not going to talk about here in detail, but
you're sneaking it in.
It's the people who say peer review is amazing, we need peer review, are not people inside science. They're not people who actually know it up close, because up close it's actually people. In fact, one thing's kind of amusing. We set up a kind of peer review system for our project, and to date, not a single person has submitted a peer review. Not a single person. It's been several months now.
Well, how can you do that?
How can we do that, Steve? Or how can people submit reviews of it?
It just says, there's just a link that says peer review. It's next to each one of our documents.
Uh-huh.
So I encourage people
open
to
source.
do it. I mean, honestly, I'm disappointed. I thought at least a few people would do it, even if they were like, I didn't really read this, but it's all nonsense anyway. But what we actually asked for, more specifically, which I think is useful, is somebody to say, I read section 3.7 and this, and I think it's correct, or I think there's this mistake in it, or whatever else.
Yeah, we have had people like Sabine Hassenfelder, an eminent scientist, and she's done a video, which is the first time you guys appeared together, where she criticizes these theories, and she's an eminent, fundamental theorist.
We've been in email correspondence with her, and she asked a bunch of questions, which were very valid questions.
Yeah, so right. So people are engaging. Yeah.
Well, wait a minute. We gave her answers, and she disappeared. So if she's still saying
that's a good
she
sign.
doesn't know what's going on,
that's a good
then
sign.
there's a problem.
Well, the fact is that you've answered her questions. She had questions that were reasonable, and that's the beginning of the process. Then if she continues to say, well, he hasn't answered my questions after he's answered the questions and she hasn't responded, then we're in a different situation.
Yeah,
but
then we can
I know
actually...
Sabina can be kind of gruff and unpleasant, but I know her to be reasonably fair in most circumstances.
Very good. Thank you guys. You guys are really spectacular. It's so generous of you to spend your time, and we got to see different sides of your ideas and try to reach some sense of different approaches that are radically different and perhaps, but they have the same common goal, which is to really introduce the world to concepts that take us out of our quotidian existence of politics, sports, and whatever. The grandest concepts. It's what
maybe we should have talked about those here. That would have been more interesting for me.
Well, let's do more where we actually treat the people who want to get into the meat of it, because I think that's
no. I was saying less meat, because I don't think this was so useful, because I think that I felt like I think we would have done better talking about kind of the culture of science and so on.
I'm sorry. I take all blame. Yes, I know. I'm sorry. It's my fault for not getting to that. Thank you, Stephen. Thank you, Eric.
Bye.
Love your work. Bye, guys.
Brian, thanks so much.
Thank you.